Hi, my name is Mario and I'm a full stack web developer and a mathematician, and today I want to talk about transformation matrix and how it works. I've seen a lot of questions online about why we need a higher dimensional matrix to do translations. So in this video, I'm going to try as best I can to answer that. The short answer is there is no translation matrix. All translations are optical illusions. Let's see why. Here we have a 2D plan. On the left, you can see our transformation matrix multiplying the initial position of our point, and the result is the new position after the transformation. Okay, to see what's happening, we need to reset our matrix to these initial values. This is the identity matrix. When you multiply any point or vector by the identity matrix, you'll get the same value. It doesn't change, and that's why we'll start here. Let's look what each value of the matrix represents. The first column is the x-axis and is represented by the green arrow. The second column is the y-axis, represented by the blue arrow. Now, the first row is relative to the x value of each axis, and the second row is the y value of each axis. When we change the first value of the first column, let's call it x of x, we're saying move in the x direction relative to the x value of each point. So, the higher the x value is, the more it will move to the right. Here, the vertical position doesn't matter because we're moving relative to the x value. Now, when we change the second value of the first column, let's call it y of x, we're saying move in the y direction relative to the x value of each point. So, the higher the x value is, the more it will move up. Again, the vertical position doesn't matter because we're moving relative to the x value. Let's reset our matrix to the identity one. Now, we want to change the second column, first row. Let's call it x of y. When we change this value, we're saying move in the x direction relative to the y value of each point. So, the higher the y value is, the more it will move to the right. Here, the horizontal position doesn't matter because we're moving relative to the y value of each point. And finally, if we change the second row of our second column, let's call it y of y, we're saying move in the y direction relative to the y value of each point. So, the higher the y value is, the more it will move up. Again, the horizontal position doesn't matter because we're still moving relative to the y value. Now, let's try to translate this square horizontally using these values. We want to translate this square to the right. We have two options. The first option is to change the x of x. But when you change the x of x, you'll have a problem because now your square is being stretched. And that's because the right side of this square have x values different from the left side. So the right side is moving more to the right. Let's try something else. Our last option is to translating using the y, the x of y. If we change the x of y, we'll still have a problem, because now the top side of our square have higher y values, so it will translate more to the right, tilting our square. Okay, so how can we translate without distortion? We need to translate relative to the same value. Therefore, we cannot use x or y. And that's why we create a higher dimension, let's call it z, where all points have the same z value. Let's move to a 3D space. You can see we have our square in space, and now we have a 3x3 matrix where the columns represents the x, y, and z axis, and the rows are the x, y, and z values of this axis. Now we can translate our square relative to the z values of each point. Here the z-axis is the blue one going up. We will need to change the x of z and the y of z, that is, the first and the second rows of our new third column. You can see that our square is translating without distortion, but only because all points have the same z value. Let's watch from above to have a 2D perspective. If we try to translate a 3D object in space, we will need a fourth dimensional matrix, because we need a common value between all points to anchor our transformation. And 3D objects have points with different x, y, and z values. And that's why we always need a higher dimensional matrix to translate objects. In linear algebra, there is no such thing as a translation matrix. All matrices are shear transformations, and a shear transformation in a higher dimension looks like a translation one dimension below. Thanks for watching, hope you enjoy it. You can lay your questions in the comment section. I'll leave the 2 links I've used for this video in the description. See you next time.